As Jennifer said, today I'll be discussing gas-liquid core tests and some of the challenges and potential difficulties or issues that may experience. So what I'll say at the start is, though, is sometimes unusual data and mismatches with what you're potentially observing in, say, log data may not be errors. It could indicate some alternative reservoir history. So I'll start off just looking at some of those. I'll start off looking at paleo contacts. And what I'll then begin to look at is the issue of gas and gas in solution. We'll look at different methods of measuring residual gas saturation. We'll look at difficulties of gas liquid relative permeabilities, and then some gas oil measurements, and put some challenges with gas oil measurements. And I think it's worth saying at the start that very often many laboratories we use gas all the time. The very basic measurements that we make use gas measurements, so that for routine core analysis, we clean the cores, we dry the cores so they're basically saturated with gas, and we perform gas measurements to determine things like grain volume, to determine gas permeability. And these are well-controlled, accurate measurements generally. And so there's a thought, potentially, we get into a thought process that gas measurements are easy. So that when that then transfers into two-phase or three-phase measurements with gas, there's the potential that we think that they're simple. But they're a little more complex than we first imagined. So I would also, at the start of this, a large portion of what I'm presenting is from a paper that I wrote together with two Society of Core Analyst colleagues, Patrick Egerman with StorNG and Arjen Senser with Shell. So there are elements that refer to that paper, and I want to thank my co-authors of the paper for allowing me to use some of their slides and agreeing to allow me to present this today. So what we might observe and what can happen in reservoir history is you may have a change in the paleo contact, or in the free water level, or your water gas or gas liquid contact. And that could be from various things. That could come from influx of water, maybe from an aquifer, or some loss of gas over time through maybe a fracture, or it could be from some thrust event that has changed the dip and the angle of and the depth of the reservoir. And so has changed the water level within the reservoir. And so what we might observe is a change in the paleo contact. So what that would look like in terms of the blue curve here is the original capillary pressure. And there's the old gas-water contact with the original capillary pressure. The green here is after there's been maybe some thrust event that has changed the gas-water contact. That the same capillary pressure curve, basically, if it's the same rock type and similar permeabilities and properties, then the same capillary curve still exists, but it's at a beginning from a new contact point. Because in capillary pressure, this point is the point of 0 PC is free water level, and the entry pressure is where we begin to is the gas water or gas liquid contact point. So what would happen then is, if there has been this thrust event, you may have water imbibition. So what will have happened is you've gone through primary imbibition, but then you would have, sorry, primary drainage, but then you would have had an imbibition process and water coming in, and you would begin to see this difference in capillary pressure and in saturation data. So you would then see trapped gas below the new gas water content. Now, if you were able to get capillary pressure data, gas water capillary pressure data from the laboratory, and you plot the saturation, say, as a function of J versus the log saturation, you will see a reasonable match for many samples, and those would be up here in the higher portions of the reservoir that are above this new contact. But then you begin to see a mismatch. And if you plotted these as a function of depth, you'd be able to see that, that these begin to diverge from being reasonably matched to the log at the point of this new water contact. And that would indicate that you potentially have trapped gas and you have a paleo contact. And we need then to think about not only drainage properties, but imbibition properties. And quite often in a gas process, many gas reservoirs are only being produced under primary production processes, depletion. And so very often we have many companies only look at the drainage process. But if you're beginning to see this sort of divergent of data, there's the potential that you not only need to look at drainage, but you also need to look at the imbibition. And so you're then going to need to look at things like residual gas and align this trapped gas content to those data. So how do we measure that? How do we scale the drainage PC to imbibition PC? Because initially it's relatively simple process. So we perform the initial capillary pressure. We may have then obtained a correlation to different reservoir properties. If you've been with us in previous webinars, we've gone through those. We've looked at capillary pressure, we've looked at saturation height modeling and the different reservoir properties that you may be able to tie those into, needing to look at different rock types that are in there. But basically what you begin to do is look at, there's a paper by Klepper et al. In '97, determining different capillary pressure scanning curves for different residual processes. So that you can begin to calculate based on where from in the original capillary pressure you are, at what pressure you finished at, to be able to calculate back what the new pressure is. And this is this imbibition saturation. So the imbibition saturation is a function of the drainage saturation divided by this term here, alpha plus SW minus my irreducible divided by 1 minus, and this is basically normalized saturation. And what that will do is will provide you this imbibition curve compared to the drainage curve. This is just showing it on a new curve, and the difference here is trapped gas saturation. And generally, the curve shape is not overly impacted by the difference in scenario. So the drainage curve for the wetting phase is usually has a very similar structure in terms of curvature as the imbibition curve. It's merely there's this change in endpoint saturation. So the endpoint saturation and residual gas saturation is then a key parameter input for these data. So how can we measure these? Well, there are a variety of different methods. My co-author, Arian Sensor, wrote a paper on this in 2014, looking at for core flooding and an improved way to perform core floods so that they're done under pressure. I'll talk about this a little bit more later, to look at what we need to do to improve these flood measurements. But there are a variety of different methods. We can do material balance, so we can either measure samples volumetrically or gravimetrically. I've discussed those in the past, in past webinars as well, how those are performed. And in situ saturation monitoring, where we use X-rays to determine the saturation within the sample by a non-invasive method. And what that allows us to do is observe changes in saturation as a function of distance across the sample. And this is an example from Maloney and Zornes. So one potentially proposed method is to determine saturation by in situ measurement, in situ monitoring. Now, one of the things is material balance, but gravimetric in particular, they're fairly cheap measurements. So you can perform potentially many measurements under with this gravimetric, whilst in situ monitoring, it's expensive equipment with X-rays or NMR. So you're needing more expensive equipment, and so these are going to be more expensive testing. And so depending on budgets, you may be limited in how many measurements that you can perform. And we would suggest that trying to do a mixture of different methods gives you an idea of the range, and we'll look at later some statistical ways to look at things like residual gas saturation. So if we're determining data from X-rays, it's always good to also have a backup check. So check and determine by a gravimetric at the end of testing, and you can determine a weight check, but also you can do a flood or extraction of the fluids and determine the fluids remaining at the end. And one of the things, another way of potentially checking these is to look at compressibility data. So at the end of my water flood, or when we've got residual gas saturation, if we've done this in a core holder, we have water saturation with some gas content remaining in the sample. Now, if that gas is under pressure, then when we release pressure, those gas bubbles will expand. And they will push water out of the sample, and that's going to change the saturation. If we compress add pressure to the system, that will compress the gas, creating smaller gas bubbles, and it may also put some of that gas into solution. We'll look at some data showing gas water solubility a little later. So one of the methods that you could use to check is by injecting a volume of liquid. As long as you know all of the volumes of your system, the dead volumes, the volume of your pore volumes, you know the volume that you're injecting, and that basically using Boyle's law and assuming relatively incompressible fluid, then any compressibility and volume injecting is because of compressibility of the gas. And so you can calculate the volume of gas based on Boyle's law. So P1V1 is P2V2. And that allows you to potentially measure the residual gas saturation in place. Then afterwards, you can also, or alongside that, you can measure the water in place. And there are a couple of methods to do that. One would be by Carl Fisher titration. The way that you would perform that is at the end of testing with only water and gas in the sample, you can do a miscible solvent injection. So a mix of toluene and methanol, and generally at least 1 litre. And the larger the pore volume and higher the water saturation, the more of this solvent mix you may need to use. Because what you want to have at the end is a miscible effluent, which is then a mix of toluene, methanol, and water. And you need to ensure you've got a homogeneous mix. So you collect the effluent, you mix it together, and you perform a Karl-Fischer titration to determine the content of water. And that can provide you a final water saturation. So we can determine final gas saturation. We can also determine the final water saturation. Or we could do Dean Stark. Now, Dean Stark requires, if it's in a core holder, we take it out of that core holder system. That means depressurizing that pore system. And so as we depressurize, we may get gas expansion, and fluid may be pushed out of the core. So what we need to do is we need to gradually reduce the pore pressure. We can't do it immediately. We need to do it in a controlled manner where we measure the expelled liquid volume so that we keep a record of how much volume is being produced out of the sample. We can then perform Dean Stark extraction, which removes the water from the core, and we measure the volume of water from that process. And that gives us another measure of water saturation at the end. And of course, we need to correct for any system volumes in that whole process. What I would also suggest is comparing your results against various of the literature correlations. So there are a few. There's this one from Suzanne et al. In 2003, where they were, in this particular case, looking at porosity. And this is maximum residual gas saturation. And we'll come on to that in a little. I'll show you some land correlations in a second, where land correlated initial saturation to residual saturation, where at some point you'll have a maximum residual saturation, and that is where the initial saturation of gas was 0. Sorry, the water saturation was 0. So you had and started off with a fully gas saturated sample. So they were correlated there, and that you can take this plot, you can look at your data and see how your gas saturation correlates as this function of porosity. Or with Pentland in 2010, as another one of the maximum residual gas saturation versus porosity. It doesn't need to be porosity. You could look at correlations of porosity or permeability or RQI or FZI, so a variety of different reservoir properties to see how your data correlates. Irwin and Batticki in '97 also looked at differences between carbonates systems and sandstones. And so what you can see here in sandstones, this is a land curve basically. So going from 0 initial gas saturation up to 100%. So this is SGRM, so maximum residual gas saturation. They saw in sandstones in general a range from 20 to maybe 45% maximum residual gas saturation, whilst in carbonates it was much higher, or potentially much higher. So there's a potential difference between carbonates and sandstones. And the land formula for correlating this is this here. So some constant is 1 over residual minus 1 over initial gas saturation. And that constant is also 1 over the maximum minus 1 to give this maximum. So the curves are going from 0 into this maximum residual gas saturation. And because many of those tests are performed, the quick and cheap test which I'll show in a minute, you can perform lots of samples potentially. And if you've got those relatively cheap tests, so it's called the countercurrent inhibition process, then we would suggest doing many plugs, obtain a cumulative frequency. So one of the processes you'll want to try and do is get data at the range of initial saturations of your reservoir, so that you can then plot those into a range of residual gas saturations. And you can do probability analysis. So plot those against cumulative frequency. And this is a P80, P50, P20, P50, P80, so that you can have that range. Different reservoir types or rock types may observe different correlations of residuals, so that it would be good to check the different lithologies that you may have and see what your P50 is for each of those. But once you've got those, you can then use the land curve to correlate then a mean and a P20, P80 from those data. And most of your reservoir is then going to lie somewhere within this saturation range. So perform compressibility tests at the end of water floods, compare the results to published compilations of maximum residual, and compare results of your measured values. So one of the main problem experienced in when we're measuring these is that we have potential solubility of gas. So gas goes into solution. To perform things like relative permeability or the residual saturation, we really need to have immiscible fluids that are not changing, that are under equilibrium. But one of the problems is, so this is just like some graphs showing you solubility of different gases as a function of temperature. This is then showing you nitrogen as a function of temperature and pressure, so that as we increase pressure, so this is 20 psi, 40, 60, 80, 100, as we increase the pressure of the water or of the system, we're pushing gas into solution, and we get higher solubility as we get higher and higher pressures. And okay, that's going to, it's going to begin to stabilize at some maximum, but you can see quite easily here, particularly close to laboratory conditions or ambient conditions, there's a large change, and this is on a log axis here. So these are significantly higher solubilities with those changing pressure. Unfortunately, when we perform tests, in order to get flow within our test, we have to have differential pressure. So we have to have a high pressure at the inlet of our core with a lower pressure at the outlet of our core plug. So that means I've got high pressure here, low pressure here. So there's the potential, if I've got this changing pressure, so at one end of the core, if I have a 100 psi differential across my core, then my solubility of gas at the start of the core is here, and at the end of the core is here. And so we have this large difference. And what that means is that as we're flooding through our test, we may be, we're starting off flowing water through the sample. We're left with some residual gas at the end of our test. But if we carry on flowing, because we have high pressure here, low pressure here, we'll be dissolving gas. If the water that we inject is not in equilibrium and is not saturated with gas itself, and even if it is, if we have a large pressure differential across our sample, we can be dissolving gas as we inject here, and the gas will then be coming out of solution as we produce the fluids outside of the plug. And so what happens is, instead of our relative permeability curve following the actual ends, we may be reading data beyond what true relative permeability is. And this is just some other data showing this. So this is a range of different water flood data from various different labs. And what I've done is calculated, this is basically a dimensionless curve, or almost. So permeability is a function of flow rate and viscosity. So viscosities here are basically very similar, of the area and length. So I'm plotting permeability times area over length. So that should be dimensionless. And if these are done correctly, what we so that we're basically using the same displacement force, equivalent displacement force, capillary number for each of these samples, what you should see is basically a tight line where the low permeabilities are done at a low rate that provide a same capillary number at the high perms, which require a higher rate to achieve the same capillary number. And so what we see here is a massive range of nominal selected injection rates. And because of that, so some of these, permeabilities at about 100 to 1,000 down here, when it's being performed at 1 milliliter, let's take this one that's 1,000, it's been performed at 1 milliliter a minute. Another one at 1,000 has been done at 3 milliliters a minute. So there's going to be 3 times higher force here. That's going to be 3 times higher differential pressure. And I correlated the differential pressure at breakthrough of all of these different samples, and what we saw was that then the residual gas saturation compared to that. And as we got over something like 10 psi, we started to see this decline in the residual gas saturation. And that's because we're beginning to now dissolve gas into the sample. And so the residual becomes not a property of the flow process, it becomes a property of how long have we continued to flow and continued to dissolve gas through the process. So my recommendation for this type of test would be perform it at something that is equivalent to reservoir advancement rates. Because if you're injecting water, your injection water is potentially not going to be saturated with the gas. And so you may have this type of effect happening, but it's going to happen at reservoir advancement rates. And so we should perform it under those sort of conditions. The other thing, one consideration I showed a webinar some months ago on relative permeability and the impact of capillary end effects. Well, that's in a non-wetting, or when you're doing imbibition with the wetting phase, and it's not fully wetting phase. So if you've got a non-water wet or even slightly oil wet case, you're impacted by the capillary end effects. And this is just showing you in a non-water wet case, the capillary end effect might look something like this, or the imbibition curve. And we're injecting water, so we're into this negative imbibition phase, because remember, capillary pressure is oil pressure minus the water pressure. And if we're injecting water, then we're applying water pressure. So we've got a 0 pressure or nominal pressure in the gas or hydrocarbon phase, higher pressure in the water phase. So we're in this portion of the curve. And so that's the curve that's going to describe the curvature and the difference in saturation observed in the test. However, if we're in a strongly water wet case, our water wet curve should look something like this. So that you have this imbibition curve coming in and to some trapped gas or trapped oil system where, well, we'll say trapped gas because this is a gas liquid that we're talking about. It's either going to be oil gas or water gas. And the whole of the negative portion is basically already at residual. And so there is negligible or potentially negligible capillary end effects when we're performing this type of test. However, because we've got changing saturation, what we should observe is that once we get to breakthrough, there should be no further production. We should hit breakthrough and then see nothing else. And that's if we've got a homogeneous sample. In the reservoir, we're not going to see that because we've got different layers, which are all going to have breakthrough at different times. But in these tests, where we've got homogeneous samples, after breakthrough, we really shouldn't be seeing any additional production. But what we see in this test is there's breakthrough, but it's continuing to continues to produce more and more, and it's just a basically linear production process. And this is what it looked like by in situ monitoring. So this is the production, this is the flood front going through the sample, pushing through, there's breakthrough, and then it's continued to produce. And what we see is this at breakthrough, we've got a nice even distribution, which is looking like what we might expect in here. But then it continues, and what we see is this incline in saturation, because now we're just dissolving gas at the start of the sample, and then that's coming out of solution towards the end of the sample because we've got lower pressures here or lower differentials, and it's not. This is not really true residual gas. The true residual gas, a real residual gas, was here at breakthrough. So when you're performing these tests, as well as controlling flow rates and trying to control the differential so you don't have too high a differential, you should also limit the injection volumes so that you're not dissolving gas. And this is the same test performed with equilibrated fluids with for a more limited time. So this was for one pore volume past breakthrough, and this is more realistic of the real residual gas saturation in this. Now, this is data from Shell. They actually equilibrated the fluids for 18 days. That was maybe a little too long. Originally, the gas was only equilibrated for 24 hours and not in a PVT equipment. It was just by flooding around the sample, around the system, and was really insufficient to get good contact between all of the gas and the water fluids and ensure equilibrium. So before doing these tests, it's always important to make sure that you've got equilibrated fluids and use proper mixing equipment to do that. So relative permeability, we'll look at some analytical models. I will also say that unsteady state is almost or basically impossible to obtain a gas, a water displacing gas, and that's because by this unsteady state, this is the sort of data I would expect. So there's breakthrough and there's no production past breakthrough. And for unsteady state to work, you have to have production past beyond breakthrough in order to calculate it. So you cannot get unsteady state relative permeability data from a water flood gas test. So what you could do though is, I'll describe this hybrid model, or you can do steady state testing, but steady state is also difficult. So here's one potential analytical model you could use. There's also one from, so this is the Corex model. There's also one from Honopour in a relative permeability monologue that he gave. So what you do is you can obtain capillary pressure, you can measure the capillary pressure, you determine a fit to the curve, you fit it by this equation here, and this is the Corey or Brooks-Corey model for capillary pressure drainage. So you also perform this normalized saturation, which is the saturation minus my residual saturation over 100 minus residual, or if you're using fractions, 1 minus the residual. And that gives me this normalized saturation. Because that's important when we then look at the drainage relative permeability. So to describe this curve, you're getting this term lambda, which is the curvature, and it's a geometric factor describing the pore size distribution for a unimodal system. So this won't work for a bimodal system. You'd have to go to something more complex like Tamiya. So the relative permeability to water is given by this normalized saturation times 2 plus 3 lambda over lambda. And the non-wetting phase or gas phase, 1 minus normalized saturation squared times 1 minus normalized saturation to the power. Oh, are people still with me? My system has just gone blank.
We are here, Jules, yes.
Okay. Is it still sharing my screen?
It kind of had a funny turn and it's flashing a bit now.
Okay, let me stop sharing and reshare. Oh yeah, so it looks as though PowerPoint just quit on me. I'll go back and reshare. It will allow me. There we go.
You're back.
Excellent. So drainage, excuse me, drainage relative permeability is given like this. And then for an imbibition process, you could use this. So my imbibition permeability to gas or non-wetting phase is given as a function of the at a given saturation is the KRG times the drainage times gas, this final gas saturation, which can be determined by this equation here. And then what you want to do is just compare those endpoints. So if you've got various different samples, compare the endpoint data. So this is the KRG at SWI, and this is the KRW at SGR. And you can see a couple of, or some outliers here. These models here were determined from that previous probabilistic probability curves of data, or similarly. So those are the bounding curves from those data, and you can see some outliers. Also, you want to check different sources of data. So relative permeability from, say, unsteady state from drainage process. So we can get unsteady state drainage gas water, but it's impossible to get unsteady state imbibition water gas. But you could then look at doing centrifuge tests of the water curve as well, and check whether they align. Or we can do the hybrid test. So how we do the hybrid test is we do the unsteady state drainage, and that gives me my drainage curve here in the blue to SWI. We then perform the countercurrent imbibition, or perform some tests to find where endpoint SGR is, my residual gas saturation. And the theory says that the relative permeability to my wetting phase is basically unaltered. it observes no hysteresis. So once I've obtained SWI, I merely come back along this, use the same curve, but it's just truncated at SGR. And from there, I can also determine what my KRW is on that point based on what that point is from the drainage curve. So that becomes my imbibition curve for water. And for the non-wetting phase, it uses the same curvature, it's just displaced by the residual saturation. It's one other method of potentially obtaining relative permeability. The other is steady state, but these need to be performed with great care. As I've mentioned, by performing injection, we've got a difference in pressure. We have to have a difference in pressure in order to have flow. And when we perform steady state, in general, you have much higher pressures because you've got two fluids flowing at once, and you also have much greater injection volumes. So rather than limiting to, say, 2 pore volumes of injection, you could have tens to hundreds of pore volumes of water injected. And so what we could observe here is some saturation data at 3 fractions, but then at this 4th fraction, then they're fairly even distribution, but at this 4th fraction, we begin to see it starts to incline. And this is because we're now moving into a dissolution process rather than just a relative immiscible displacement. And in terms of the differential pressure, so that's the pressure for the first stage, the pressure for the second stage, the pressure for the third stage, and for the 4th fraction, the 4th stage, that's where we began to see data above this 10 psi limit, where we're now getting into larger and larger differential pressures, and so larger potential for dissolution and solubility of gas in here. The other problem with steady state floods is that because it's strongly controlled by the wettability, and it's often very difficult to obtain data within these early fractions, and the steady state data process is basically designed to try and give a wider range of saturation, but because water under strong wetting conditions is just pulled into the pore spaces, and the gas has no force to keep the water at bay. It has the water is just pulled in. There's often insufficient gas pressure to keep the water out, and so we begin to get this large saturation change at these early stages. And you have to begin to go, so the fractional flow of this curve here, this is simulated, was 0.0001. That would take about 7 days to obtain that one stage of the curve, and then each of these take less than a day to perform. But because the injection here is so slow, and it's the only way of getting these early fractions, and to go any slower than this, you would be looking at 1 month for one step, and that's just impractical. So one of the methods that you might use is exchange gas for decane or some light alkane, heptane, hexane, or something similar, and perform it with there, because then the liquid has, although it's non-wetting, will have some resistance against the water. Okay, so finally, gas oil, and one of the problems of doing gas oil measurements, I mentioned this in a previous webinar as well, that because of interfacial tension differences between the different fluid phases, when you're performing gas oil, you also have water in place at residual. And often it was established using oil-water SWI or an oil-water pressure to obtain SWI. But then when we go with a gas water, the gas, sorry, a gas oil, the equivalent pressure from Young Laplace IFT perspective, the equivalent pressure of gas water is much higher, or water oil is much higher than the pressure that we're actually wanting to apply. And so there's a potential that we begin to produce water. And this is data from one sample showing that. So the blue in here was a centrifuge process of oil water to obtain SWI. And then a gas oil test was performed. And what we see is it's generally overlaying the water fairly well. There's some fluctuations because of uncertainties or just general measurement error in the data. But what we see is suddenly here in these last two tests, there's a divergence in the test data. The oil is suddenly higher. And what you observe in the data here, so 9.1 cc's of water was drained out the sample to get to SWI. But when the gas oil test was done, 9.28 volume of oil was obtained. Now that can't be, because only 9.1 cc of oil went into the sample. So how can we obtain 9.3 almost cc's of oil out? Well, it's because at this stage here, it's where the gas oil, the equivalent oil water pressure from the gas oil test exceeded the original oil water pressure used to establish SWI. So at this stage here, it's not only it's not only oil we're producing oil plus a very minor amount of water. It's only 0.42 cc of water. So it's a fairly small volume, but it's 0.4 saturation, or it's 4 saturation units, or 0.04 fractional saturation. So it's significant and means that there's this mismatch. But when you correct for any water that's produced, because we did Dean Stark at the end to determine the saturation. So a saturation before testing was 13%. At the end of the test, the saturation was only 9%. So we've lost 4% of the saturation. And when you correct for this, then you get a more realistic data, and the residual gas would have been negative, but originally, but once you've corrected and accounted for the water production, the residual oil would have been negative. The residual oil is actually 6%. So in conclusion, use drainage capillary pressures to derive your imbibition curves. Ensure that you understand what your residual gas is. Put appropriate checks and cross checks in place so that you can determine and get more accurate. Use cheap and fast measurements, because you can do many measurements and get a good probability curve of all the different data. The porous plate technique is often recommended, because there you can have gas pressures and fluid pressures and maintain all of the pressures, but it requires reservoir or higher pressures, and not so many labs can do that. And if you're doing unsteady state tests, then ensure that your fluids are equilibrated for at least 24 hours, generally up to 2 days, or with proper PVT mixing equipment to ensure that you've got actual equilibrium between the fluids. Use low flow rates, limit your differential pressures, and limit your injection volumes. And potentially use in situ monitoring if necessary, and confirm with cross checks afterwards. And for steady state experiments, generally not recommended gas water systems under limited pressure. We would suggest doing them at higher pressures, or you can change out the gas for one of these light alkane hydrocarbons. But try and limit the differential pressures, which requires limiting flow rates and optimize the fractional flow rates that you apply to try and get those lower saturations, but that may take time. So again, would like to thank the co-authors of the original paper for allowing me to present this again, and I will now take any questions. Hello, Jennifer, are you? I can't see the questions at the moment.
I am here, Jules. Your screen seems to have stalled. Not your presentation screen, but your video screen. But
oh, okay.
That's okay. We can still hear you. Okay. I've got a few questions.
Maybe not.
No, it's gone blank now. I've got a few questions that came in prior. If you want me to put these to you now. Andrew, what is the best method to generate trapped gas saturations from core measurements?
So hopefully the presentation has answered a bit of that. So
okay.
So performing it by a number of different methods. So and then comparing them, you can perform this countercurrent imbibition. That's the cheap gravimetric process. You place the sample under toluene or the formation water and allow it to imbibe and obtain the residual saturation from those tests, or to do it by this low rate unsteady state injection process with limited differential and limited injection volumes.
You may have covered some others already. I'll just read them out just to check. How do you have relative permeability for WAG injection and for three-phase flow?
Generally, you obtain the relative permeability of WAG from performing the different fluid pairs. So you will obtain an oil-water relative permeability, and those data you'll get gas oil and gas water. Find the residual limits of each of those, and there are a number of different models and correlations that could be used to cross-correlate between whether you're in a strongly water-wet conditions or you're in mixed wet. So there's the Stone's method. So there's a variety of different models that might be used to convert the three two-phase systems into three-phase rel perm.
I had another one through here. The differences between co-current and current imbibition to measure trapped gas.
So maybe I should have included. I thought I did have a screenshot of co-current and countercurrent. So in co-current injection, what you're doing is you're inject the production is in the same direction as the flow. So you'll be injecting water, maybe, or just allowing it to contact the sample and flow, and the sample will be in a core holder, and flow will always be in this direction or in this direction, depending on whether you're injecting water or injecting gas. So co-current injection is when you obtain effluents and production in the same direction as flow. Countercurrent imbibition would be where you place the sample, say, under a fluid. The sample is saturated with gas or a hydrocarbon, and that because it's if it's not oil wet, If it's water wet or any form of oil, water wetness, water will be drawn into the sample. So water is going in, that's the direction of the displacement flow, but the oil has to come out. So the hydrocarbon gas is coming out. So that's then in the opposite direction, or it's counter the injection current. So that's counter current imbibition. And that can be done either under a fluid, or it can be also done in a core holder. So you can perform counter current testing in a core holder, but what you're basically doing is you're not flowing through the sample. You're just flowing across the surface of the sample, and imbibition is going to happen in one direction and production is happening in the opposite direction.
Perfect. I can't see any other questions in the Q&A.
There's one that says, how did you measure saturation in the figures I showed? So
Oh, yeah.
there are a variety of different ways. If I go back to, so in this, this is a centrifuge. So in the centrifuge process, we have a camera fitted to the centrifuge, which is monitoring a small production window so that we can see the changes in interface between fluids in that window. So that allows us to monitor there. In tests like this, these are by in situ monitoring with X-rays, and then other ways. So this test here, that some of these data are either done by just gravimetrics or by volume, so that we also, so as well as monitoring it here by volume with a camera, we have the volumes at the end, so that we can check the volumes at the end, or we have the weights of the samples and we can check the weight of the samples at the end as well.
Okay, great, Jules. I think we will wrap up now because we're just about on time as well, and I can't see any other questions.
There's one coming into chat, which is why we're not seeing it in the questions. So there's one that says, have I seen the experiment called partly countercurrent? Is it different to countercurrent? And yes, so partly countercurrent, depending on how you have your experiment set up, if you have, say, water coming across the surface of the plug, around the tube and across the surface at the top, then you could have both countercurrent and co-current happening at the same time. So at one end you'll have countercurrent, and at the other end you may have co-current. And so it depends how you've set your experiment up. And there's one other question come in from Machaba. How is it possible to eliminate the capillary end effect at low flow rates? Well, that's one of the things that I was saying. Often with a gas test, because we're talking gas testing, with gas testing, the capillary, there is little capillary end effect, because I think I showed that the capillary, it was early on, basically showing for a water wet case, the capillary pressure for imbibition in the imbibition core flood, where we've got negative capillary pressure because we're injecting, basically you're in this part of the capillary where you've got even saturation across the whole section. So you have even distribution across the sample, and there's little or no capillary artifacts or capillary pressure effects from those low rate tests. It's different. So gas testing is different than when you're doing oil testing because of the wettabilities. If we were doing it in a drainage mode though, so we're injecting gas and it's water wet, the gas is trying to push against water. The sample is trying to hold on to water because that's what capillary pressure is doing. Capillary pressure sucks. It's pulling onto water or sucking the water, not allowing the gas to displace it out. And so when we're doing a gas displacing liquid, you will have very strong capillary end effects. But when you're doing water displacing gas, they're basically minimal or nothing.
Okay, thank you very much, Jules, and thank you everyone for joining us. We'll just wrap up quickly now. It's run a little bit over, but if you do have any further questions, just feel free to get in touch with Jules or myself, and we'll be happy to follow up with you after session as well. We'll also get a link sent out to you tomorrow with today's recording, so keep a lookout for that one coming through in your emails. If you do want to catch any of our previous sessions you might have missed, then you can actually check these all out on our Premier Corex YouTube channel. If you just search Premier Corex on there, then all of our sessions will be available for you. We've had some great topics over the months, so it's full of really great content for you to have a look at. Just doing a quick look forward at what we have coming up, you'll see on your screens there, Justin, who you'll know from the FD series, and Jules will be back on the 20th of May with something that, as we all know, is a very hot topic currently at the moment, looking at carbon capture storage. And then we have a new speaker to the agenda on the 14th of June, which will be great, with Dr. Ahmed Salah from our Premier Oilfield Group Egypt office, looking at permeability prediction from NMR and MICP. So that's set to be a good one there. All of the upcoming registration details will be on our Premier Corex LinkedIn and social pages as usual, so do keep a lookout for those coming up soon. While you're there, if you give our page a quick follow as well, that means you won't miss any of the future sessions and our news. I think that's all from me. Thank you to Jules, and yeah, thank you again for joining us and hanging on just a few minutes over there. We hope you can make it for more of our sessions in the coming months. Thank you, everybody.